My name is Daniel Berrange, and I'm the lead developer on the Libvirt project. And I'm going to talk to you a bit about what Libvirt is, what it can do, what benefits it brings to KVM, and a little bit about what we're planning in the near future. So there's a number of reasons why Libvirt exists. We want an API that is stable across hypervisor changes so that when new releases of QEMU or whatever platform comes out, your applications continue to work without any changes required. We want a standard API, so something that works across many different hypervisors. We want something that is simple. So if you look at models like the SIM DMTF virtualization APIs, those can be quite hard to get started with, so a bit of a burden for application developers. Libvirt tries to get you running quite quickly. It's a portable API, and by portable I mean Linux has the full range of functionality and the other operating systems have some degree of functionality, mostly just client side. It provides a secure mechanism to manage the hypervisor hosts from remotely across the network, and of course it's under an open source LGPL license. The Libvirt community has grown since it was initially started by Daniel Veyard, and we've now got contributions and major development work from a large number of companies. From every major Linux distribution has people contributing, and there's many independent contributors who are unaffiliated. So what virtualization technologies do we support in Libvirt? Libvirt has a pluggable driver mechanism, so we can support different hypervisors, and QEMU, what we call the QEMU driver, supports basic QEMU functionality and also KVM, and that's probably our most comprehensively supported hypervisor driver in Libvirt. In terms of features, the next most featureful one is the VMware driver, followed by the Zen driver. And more recently, we've started doing a bit more active work on LXC, which is making use of the native Linux container functionality. We also have a test hypervisor, which is basically just an in-memory stub of all of the APIs. And this is very useful for application developers who want to just test out their application's functionality in an isolated environment with predictable results. So we use this test hypervisor driver for doing a lot of automated testing on the Virt Manager application as an example. And finally, our what we call the remote driver. This is a general RPC layer that we use to remotely access any Libvirt driver from across the network. There's several more drivers that are in various stages of development: VirtualBox, OpenVZ, IBM Power Hypervisor, user mode Linux, believe it or not, Zen API, and in the not too distant future, Hyper-V as well. So we pretty much got all bases covered in terms of virtualization technologies out there. What platforms? I mentioned a few minutes ago that Linux is the primary platform for pretty much all of our development, so it should come as no surprise that Linux has by far the best platform support in Libvirt. For OS X, we currently only support it as the RPC client, so you can use an OS X client to manage a Linux virtualization host. Windows, we also support as an RPC client and as a host for managing VMware instances and VirtualBox, and soon Hyper-V. And finally, Solaris is supported as a RPC client, and at some point in the past has also been able to work as a Zen host driver, but I'm not sure if that still works or not. And I should have mentioned the BSDs. There's a couple of guys who maintain the BSD ports for us. So Libvirt is much more than just a hypervisor management API, because when you're writing an application, you want to deploy some guests, you need to do more than just start the guest and control the guest's operation. You need to provision storage for the guest, you need to connect it up to the host network in some way, you want to do PCI device pass-through, and all sorts of other things like that. So we have a number of different areas of the API which are also done with pluggable drivers. So in the storage area, we've got APIs and drivers which support managing LVM logical volumes, volume groups, creating volume groups, creating logical volumes from the group, and so forth. Disk partitioning, so you can take a block device, partition it as you wish. SCSI and iSCSI, so you can create MPIV SCSI virtual adapters and enumerate the LUNs within them. And you can also enumerate the LUNs in your fiber channel adapters that are in your host. For iSCSI, we support logging into a remote iSCSI target, enumerating the LUNs. And for NFS, we can mount remote NFS volumes, and the files within the NFS directory can be used as backing store for the guest disks. There's a few more things with storage, but the general idea is that we have plugins for different types of storage for connecting to the storage and enumerating the volumes within that storage group. In terms of networking, we can, on a Linux host at least, on Fedora and RHEL in particular, we've got APIs which let you configure physical network interfaces, configure bonding between interfaces, configure VLANs within the interfaces, and set up bridges on your interfaces. And more recently, we also gained support for integrating with VEPA. So you're kind of offloading the bridging to the network switch. One of the other useful things you can do, it's kind of related to networking, is using our Firewalling Driver. This integrates with IP tables and EB tables, and it allows you to control the traffic that a guest virtual network interface can send and receive. So at the very least, you can do protection for IP spoofing and MAC address spoofing, but you can also do, pretty much any type of filtering you can do with IP tables. You can find a way to do a lot of that functionality within the Libvirt API, and it will do things like it will if you nominate a trusted DHCP server, it will look at the responses from the DHCP server to figure out what IP address a guest is being assigned, and then it can automatically set up further filters based on the IP address of the guest. That can be quite useful for certain scenarios. When you're doing PCI device assignment or USB device assignment, you obviously want to be able to find out what devices are available on your physical host that can be assigned to the guest. So we have a host device enumeration API, and this uses, in the old days it used HAL, in the new world it uses UDEV. And you can get a complete device tree telling you all about all the physical hardware in your host. And for PCI devices, it'll let you attach and detach the PCI device from the PCI stub driver, so you can safely hand it to the guest OS. And it also takes care of things like being able to reset the PCI device before giving it to the guest. The last thing on the list there is what we tend to refer to as SVIRT. And this is basically a mandatory access control driver that's built into the QEMU driver within Libvirt. And what this does is it ensures that every QEMU instance you launch up is running under a dedicated security profile. So that ensures that the guest OS, even in the event of a QEMU compromise, can only access host resources that have been explicitly assigned to the guest. And this is in addition to also running QEMU as an unprivileged user ID and various other things that I'll talk a bit more about security later in the slides, actually. Just a very simple diagram to illustrate the kind of general architecture of Libvirt. On the virtualization host, on the far side there, you typically have what we call the Libvirt daemon running, and this is where most of the hypervisor drivers live if they're stateful drivers. And each driver will talk to whatever pieces of the host platform are necessary for that virtualization technology. So, for example, in the Zen driver, Libvirt talks to Zendy, ZenStore, and the hypervisor directly. In the case of the QEMU driver, we talk just to the QEMU process via the QEMU monitor. There's no other supporting daemons that really need to be talked to there. And then on the other side, we've got the client host, and this is where the application will provide a URI which identifies what hypervisor they want to talk to and on what host it's located. And depending on the URI you give, it'll activate a different Libvirt driver. So most of the time, if you're on the client host, it'll first activate the remote driver, which is our RPC system, and that RPC system will then forward all of the API calls to the Libvirt daemon on the actual virtualization host, which is where all the real work takes place. One or two of the drivers, notably the ESX driver and the VirtualBox driver, actually don't need to use the Libvirt daemon because they can talk directly to an equivalent daemon provided by VMware or VirtualBox. But for QEMU or KVM, you've definitely got this Libvirt daemon, which is where all the interesting work takes place, and then the client, which is just a thin RPC stub. So how can you make use of the Libvirt library? Well, the core library is basically just a standard C shared library, so you can link to that and call the APIs as you would with any normal C program. We've also got bindings to all of the main programming languages: Perl, Python, Java, Ruby, OCaml, C#. Most of them are pretty complete and pretty well maintained, so you've got pretty good choice of languages to use Libvirt from. If you have an application that is already designed around the idea of using the SIM DMTF model for managing virtualization hosts, then we've got an agent called the Libvirt SIM Agent, which maps the Libvirt API into the DMTF virtualization schema. So that's another way to consume the Libvirt API. If you're using the AMQP message bus and something like QMF, which is the object modeling system built on top of AMQP, then we've got an agent called Libvirt QMF, which again maps the Libvirt API into this alternate object model. Most recently, we just started a Snmp agent, which again maps. So far, that's just mostly focusing on the hypervisor APIs, just mapping them into Snmp, so you can enumerate guests and do a few basic operations on them, get performance stats. And lastly, this is the most recent bit of work we've started on, is binding Libvirt into the G-object model. And the reason for doing this is to make it easier to consume Libvirt in desktop applications, which are typically, at least in a GTK GNOME world, built around G-objects and So we think that's a very useful technology for integrating Libvirt with the desktop. Just a few examples of applications which are using Libvirt today. We've got the simple things like virt install, which is a command line provisioning tool, virt manager, which is a smaller scale desktop management application for managing a handful of hosts on an ad hoc basis. Cobbler is a network installation service, and that has a Libvirt plugin for provisioning guests directly. RHN uses Libvirt for doing entitlement checking for virtual guests. RevM and VDSM is now using Libvirt for all of its hypervisor management APIs, and that's the subject of the talk following this one. The Gnome Shell, if you've been brave enough to try out Gnome 3, you'll know about the Gnome Shell. And we've got a proof of concept, which is integrating virtualization into the Gnome Shell experience. So your virtual machines just appear directly within the Gnome Shell, and you see the screenshots of them and launch them up without. So the idea there is you have a desktop integration of virtualization, so you haven't got some separate standalone virtualization management app. Virtualization is a native built-in feature of your desktop, is the idea there. That's very much a proof of concept at this time. And then the last one is just one fun tool I put in there, which is virt dmessage. That uses Libvirt to peek inside the guest memory and pull out the dmessage logs. And the nice thing about this is it works even if the Linux guest is completely crashed or hung. So it can be quite useful as a debugging tool. So now I want to spend a couple of slides just talking about some of the benefits of using Libvirt as opposed to talking directly to the QEMU monitor and doing everything yourself. The first one there is CPU ID validation. So for every guest, you can assign a CPU model to the guest, and when it comes time to migrate the guest to another host, before the migration takes place, Libvirt will check the compatibility of the CPU that the guest is currently using against the destination host. And if those CPU types are not compatible, then it will refuse the migration rather than just allowing the migration to proceed and have the guest crash sometime later. So that's quite useful. The native QEMU migration data transport just uses a plain TCP socket, which is great if you've got a trusted LAN between your hosts you're migrating across. But if you want to migrate your guest across a network where you don't trust the network, then you might want some encryption there. So Libvirt provides a way to tunnel the migration data stream via the Libvirt daemon. Because the Libvirt daemon already has security features built in, we can take advantage of those to secure the migration data stream. One of the features we worked quite hard at was ensuring that whenever we launch a QEMU guest, we know exactly what ABI is going to be exposed to the guest, and we can work very hard to ensure that ABI is the same every time the guest is started. At the simplest, this means making sure that the network devices and block devices have the same PCI address every time you start QEMU. This is particularly important when you're doing migration because you don't want your network card to move from slot 3 to slot 5 when you migrate your guest across different hosts, as the guest OS tends to get unhappy with that. One of the main goals of Libvirt is to provide a way to describe your guest configuration in a way that is stable across different hypervisors and across different releases of the hypervisor. So what this means is you're abstracted from the details of how QEMU actually launches a guest. So as an example, originally when you were specifying disks to QEMU, you might use the -HDA command line argument. Sometime later, QEMU invents this new -drive argument. A few more releases, you now are recommended to use -drive and -device. And in a future QEMU release, we might have yet another way to specify how you configure disks. One of the benefits of using Libvirt is that Libvirt can be updated to follow the latest KVM best practices for launching guests, and your applications just get the benefit of that immediately without having to have any changes. So if the application is using Libvirt, you know you're going to be in close compliance with the KVM best practices at the time. Again, the same kind of thing for the monitor. Over time, the way you interact with the QEMU monitor has changed, most notably from a text-based human interactive monitor to a JSON-based monitor. We ported Libvirt to use the JSON-based monitor as it was being developed in QEMU. And when it became featureful enough for us to use, we switched Libvirt to use the JSON monitor by default. So this benefits any application that is using Libvirt is now using the QEMU JSON monitor, which is the best practice at this point in time. So again, the application has been isolated from the specific implementation detail in QEMU. So you just get to focus on the important things for the application instead of changing QEMU targets. The final point there is save restore. So this is saving the VM state to a file on disk and then restoring it at some point later. QEMU can do this natively via its migrate command. When we do this via Libvirt, there's a couple of extra things we can slot in there. So we can add in a compression program, which will dramatically reduce the size of the saved state file on disk. And about a month ago, we also added support for using ODirect when you're saving the guest to disk, so you don't pollute the page cache. Now, there's a few other benefits related to configuring resources and managing resources relating to the virtual machine. On modern kernels, Libvirt will ensure that each QEMU process is started within a dedicated C group. So we can then use those C groups to apply resource constraints to disk I/O, memory usage, CPU scheduling controls, things like that. So we provide APIs for managing the guest resources that are backed by C groups in this case. For networking, although there is a C group controller that can do networking, we actually chose to directly integrate with the Linux traffic shaping tools. The reason for this is that if you use the C groups for controlling networking, then the entire virtual machine the network controls will be applying to the entire virtual machine, but we actually wanted the network controls to apply to each virtual network interface you've assigned to a guest. So we did that directly using the traffic shaping tools. When it comes to launching QEMU instances with disks, QEMU doesn't make any attempt to stop you doing stupid things. So you can quite happily launch two QEMU instances, pointing them at the same disk, and have them both fight over writes, and you'll pretty soon get disk corruption, file system corruption in your guest. So fairly recently, in the past 2 months or so, Libvirt introduced a framework for doing exclusive locking over guest disk images. So when you start up a guest, Libvirt will acquire a lease on any disks that are assigned to that guest, and that'll prevent any other guests using those disks at the same time, or prevent the same guest being started twice on different machines. This is actually a pluggable framework, so we've got two different implementations of this. One using a technology called SANlock, which uses a disk packsource algorithm for doing locking, and another simpler implementation we did in Libvirt, which just uses the POSIX FCNTL locks. One of the other sets of APIs in Libvirt is for managing encryption keys. This is useful with QCOW disk images. So you can configure a guest to have encrypted disks, and when you start that, you can have that guest configured, and it can be visible on multiple hosts. But you won't actually be able to start the guest on any host unless you've set the encryption key for that disk on that guest on that host. And the QCOW encryption stuff is particularly useful if your network file system is something that you don't trust. So, for example, if you're using NFS and you don't want your storage administrator to have access to the guest data, then you can use the QCOW encryption capabilities to secure your guest disk images. And this is actually better than doing encryption inside the guest in some ways, because if you're doing encryption inside the guest, then you've got the problem of how do you provide the keys to unlock the guest disk images when you boot up the guest. If you manage the encryption keys on the host and use the QCOW encryption, then you can have a management service that controls the keys and automatically provides the keys to the guest at the right place at the right time. And finally, on this slide, Pci Device Assignment. There's a lot of things that can go wrong when you're doing Pci Device Assignment, and there's a lot of constraints that you have to make sure you don't violate, particularly when it comes to things like resetting the PCI device before giving it to the guest. Depending on the PCI topology and PCI features, there are various different ways you can try to reset a device. And Libvirt will examine that and take care of figuring out which is the best way to reset a PCI device and assign it to a guest without causing trouble for the rest of the system.
5 more minutes.
Okay. In terms of security benefits, I mentioned already that we have a flexible framework where we can apply mandatory access control for guests that isolates each individual QEMU process. We also run QEMU as an unprivileged user ID, and we've got plans to make it so that you can run each QEMU instance as a separate user ID in the future. We use the Linux capabilities to block all the use of set UID programs from QEMU. So in the event of QEMU being compromised, it can't use a set UID program to escalate its privileges. We use the cgroups device controller to set a whitelist of what block devices a QEMU process can access. And as part of the common criteria certification work we've done with Libvirt, we also added auditing to all of the critical operations. So anytime a QEMU process is assigned a host resource, there's an audit log of saying what was assigned to what guest. And one of the areas we'd like to explore in the not too distant future is making use of some of the Linux container facilities or namespace facilities to further restrict what the QEMU process is able to do on the host. A couple of things I just wanted to mention that can be useful for KVM developers is a lot of our work is focused around end users, and we've had feedback from the KVM developers, a community in particular, that it can be hard to do certain things with Libvirt if you just want to hack around with certain things that aren't directly supported. So we've added the ability to pass through arbitrary command line arguments in the guest configuration and arbitrary environment variables. We also now have the ability to send arbitrary monitor commands to a guest, either using the JSON syntax, or Libvirt can accept the human monitor syntax and automatically convert that into a JSON HMP pass-through command. And most recently of all, we've added the ability to attach Libvirt to an externally launched KVM instance. So you can launch up a KVM instance with whatever command line arguments you absolutely want, and then tell Libvirt, here is the PID of that KVM instance, go and connect to its monitor and manage it. I should mention, though, that these features do come with some support caveats. Depending on your OS vendor, they may or may not support use of these features in a production deployment. So we mostly have done this for developers and ad hoc testing and debugging and troubleshooting. if you actually want to use a certain feature in a production deployment of KVM and Libvirt, then we still recommend that you use one of the supported interfaces for doing that. And if it doesn't exist, then send us a feature request and we'll do our best to add support for that. Just a quick list of things that we'd like to do with Libvirt in the not too distant future. Role-based access control is something that we'd really like to add, so that you can say on a, the idea is to be able to set access controls on a per VM, per operation, per user basis, who can do what. And also integrate that with SE Linux, so you'll have Libvirt doing SE Linux checks on each individual operation and that is carried out on a guest, which we think will be quite compelling for certain usage scenarios. We want to do more work with scalability to make sure that Libvirt isn't the bottleneck in any of the management areas. We want to make sure QEMU or someone else is the bottleneck. With the storage APIs, we have the ability to discover various types of storage and talk storage and find out about what LUNs are available in an iSCSI target, but it's really frustrating not being able to actually create LUNs for an iSCSI target because there's no standard iSCSI protocol for doing that. But various vendors have got custom extensions for allowing LUN creation on their iSCSI targets, so we'd like to explore whether we can integrate with some of those to enable iSCSI LUN creation via the Libvirt storage APIs. And the last item is something I mentioned a few slides back, is we're working on binding Libvirt to the G-object type system, primarily for the desktop use cases, but in parallel with that, we also want to create a new library, which I'm calling Libvirt gconfig. And this is basically just a set of classes and methods for building up configuration descriptions of virtual machines. Because if you've used Libvirt in the past, you'll know that all configuration is done via XML files. And people can find that kind of hard to manipulate those. So we want to provide an API for actually creating these XML descriptions. So you can just use a plain object-oriented API for configuring things. Lib Os Info is a simple database of information about operating systems and hypervisors and what their supported hardware is. So you can be able to know if you're deploying on QEMU version 0.15 and you're deploying a RHEL 6 guest, you can ask Lib Os Info, well, what is the supported hardware for this combination? And it can tell you that you should be using VirtIO block and VirtIO net or what have you. So it's just useful. Everyone has to solve these problems when they're building a management tool, so we want to provide an API to allow you to query this information. And the last one there, Libvirt install, is a library intended to make it easier to deploy guests by just taking care of some of the general legwork that you have to do as a management application when you deploy new guests. Everyone has to do the same kind of logic there, so we want to put it together into a library that anyone can reuse.
Yeah, I think that's going to have to be the last slide, so I think we can probably do one question.
Okay, so I had a few slides on libguestfs, but they'll just have to be passed over. But yeah, question?